second in the Physics Notes series for Unit 9, Modern Physics. We'll talk a little bit, review a little bit about what we spoke about last time. So last time we just talked about black body radiation, atomic theory, the Bohr model specifically, energy level diagrams, and Planck's work, where E is the difference between the energies, and then E equals hf, the energy of the photon. A little bit about spectroscopy and how that was instrumental in finding Bohr's work. So I want to continue on with this today. So again, this is the energy level diagram off the reference table. So an electron in its ground state has an energy of 13.6, and an energy where it's an electron that's ionized, where the energy is, or the electron is totally removed from the atom, has an energy of 0. So to take it from its ground state to 0 is 13.6 electron volts. That is also known as the ionization energy. It's the energy needed to remove the electron from the atom. So that's really kind of important for our next thing, which is the photoelectric effect. So photoelectric effect found that when light shone on metal, electrons can be emitted from that surface. So here's a light down here shining on the metal. We get the ejected electrons. So the energy that these electrons move away with is a function, and that's the energy these move away with, the kinetic energy, is a function of the frequency that the light comes in at times Planck's constant minus this Planck's constant times a threshold frequency. The threshold frequency is the work function. It's the energy needed to remove the electron. It's also known as the ionization energy. So if we're specifically looking for hydrogen, that work function or ionization energy would be 13.6. So if I put in 15 electron volts of energy, it would have enough energy to bump it up out of its orbitals, and then it would be carried away with the leftover, which is 1.4. Again, if I take that back to this equation and take a look at how that relates to what we're talking about. So if this was 15, that's the amount of energy that came in, and it took 13.6 to take it off, to ionize it, then the leftover would be 1.4. So again, that work function is also known as the ionization energy. It's the energy needed to eject the electrons. Now, you will have an activity where you're going to have to create a graph of frequency versus energy, and it's going to have an outcome of something like this. So again, the energy is ejected is based on the frequency. The total number of electrons is based on the intensity of light. So previously, the classical model said that if you have a brighter light or more intensity of your light, you'll get more energy that's released. That's not true. You get more electrons that's released, but the energy that travels along with the electrons is based on the frequency of the incoming light, not the intensity of the light. So this is a great FET, but it's unfortunately a Java FET, so it doesn't work on your devices. But this is a picture of that FET where you can manipulate the frequency or the intensity. Here it's showing the intensity increasing. As you get more intensity, you get more electrons ejected. You can also manipulate the frequency, and if you get red, you get lower frequency, thus lower energy. So if you move it down to this red spectrum, you don't even get electrons ejected at all. You move it up to the violet, and you get electrons that are ejected with very high energy. So this is one of Einstein's, not one of his most famous works, but one of his most notable works. He did win the Nobel Prize for this, and and he did a lot of other great work that he didn't win the Nobel Prize for. So this is the work based on the work of Planck that we talked about, and Einstein didn't even test this. He did a thought experiment for it, and the work was later verified by Millikan. Again, this is photoelectric effect, which is really convincing evidence that light is quantized rather than a classical model. So quantum mechanics is a study that pulls together the wave particle duality. Another example of this is Compton Effect. So when we had Compton Effect, what we have is we have an incident photon or light that comes in and it actually hits a particle. when it hits the particle, it then scatters. It moves the particle and it changes the incident photon. So notice here we have a photon with high frequency or low wavelength. Here we have a photon with lower frequency, thus lower energy. Well, why does it have lower energy? Because it gave some of that energy to the scattered particle. So what this is showing is the photon, the light, when it hit a small enough particle, it actually moved the particle. So light can make things move, which is, a very, it was a big revolutionary piece of work by Compton. Furthermore, and this is kind of deep, we talked about before that if we have double slit diffraction on light waves, that you get a diffraction pattern that shows up. So like you would expect if you shot then particles, the particles would then go straight through the slits and show up right on the screen behind it. But that's not what de Broglie experienced. So de Broglie found if he sent electrons through, we got the same kind of diffraction pattern that we got for light. So what de Broglie showed is that Young showed that waves had these diffraction patterns. De Broglie showed that particles too exhibited wave properties and showed these diffraction patterns. So de Broglie said that all matter has both wave and particle properties. So the wavelength, so if I look at this, we don't experience these wave properties for particles because they're so incredibly small and we cannot detect them. So if you took the mass of a baseball times the velocity of like 10 meters per second and then divided that by Planck's constant, which is 6.63 times 10 to the negative 34th, you get a number that's incredibly, incredibly small. At some point in the future, we may be able to detect that, but with the instrumentation that we currently have, we cannot detect wavelengths of particles at this point. So furthermore, you could change this around, manipulate the momentum and bring it up, and you can get energy equals PC. Heisenberg uncertainty principle is one of the foundational thoughts of quantum mechanics. So what Heisenberg said is you cannot know the momentum or the position of an electron concurrently. So your degree of certainty about knowing the position decreases your degree of certainty about knowing the momentum, and vice versa. The more you know about momentum, the less you know about position. And again, as you go into college physics, you'll learn much more about these quantum principles, and Heisenberg's uncertainty will be key to that. So as we continue, we're talking about nuclear physics here. There's a great deal of overlap with chemistry here. A lot of courses teach us in a chemistry course rather than a physics course. Again, we're going to revisit some of the work of Einstein. His famous equation that relates mass to energy is E equals mc squared, where E is the energy that results if you can convert mass to energy. Now, C is the speed of light, which is 3 times 10 to the 8th, as we learned in the last unit, squared. So energy is measured in joules, mass kilograms, C is meters per second. So that's dimensionally sound. This is a conversion that you also have on your reference table. 1 atomic mass unit equals 931 mega electron volts. And you may need that moving forward. You will need that moving forward on the comprehensive worksheet. And again, because it's on the Regents reference table, you likely will need questions like that. And mega means times 10 to the 6th. So this is really 9.31. We'll take 2 exponents there and then 6 more there gives us 8. So mega electron volts is kind of an unusual unit to work with. This is a more usable form of this conversion, but again, this is what you have on the reference table. So an atomic mass unit is the approximate mass of a proton or neutron. There was a Edpuzzle that spoke of this too. So now this is a hypothetical situation. We very rarely are able to take the total mass and convert it to energy, but this is the scenario. mass of electron is totally converted to energy. How much energy would there be? So mass of electron on the reference table times 3 times 10 to the 8th squared gives you 8.2 times 10 to the negative 14th joules, which again is a lot of energy for this conversion. This is a huge number, but because this is so small, this still results in a relatively small number here. Where we're more likely to see this is, mass of proton, similar equation. I get, this is the mass of the proton, 1.67 off the reference table. And then if I were to convert this to electron volts, I could say, well, that's my energy in joules. I'm going to bring it down here. And my conversion factor is, for 1 electron volt, I get 1.6 times 10 to the negative 19th joules. That should have joules there, but it doesn't. And I can then convert that and get 9.3 times 10 to the 8th electron volts, or, as we spoke about on the last slide, 1 U equals 9.31 times 10 to the second mega electron volts. So I could also do the conversion for that. So where we're more likely to see this in the real world is the fact that an atom, so we're looking at a helium atom here with 2 protons, 2 neutrons, and 2 electrons, as compared to 1 proton, 1 electron, 1 neutron, 1 proton, 1 electron, 1 neutron. So basically, this has 6 particles. This has 6 particles, the exact same 6 particles, but the mass of the particles individually is greater than the mass of the particles that when we get here. So basically what happens is, as we take these particles and put them together into an atom, some of that mass gets converted to binding energy. So likewise, we can take, when we split atoms into split into daughter cells into smaller atoms, we release energy through that process. So again, there's a mass differential. That mass differential is due to some of that mass being stored as binding energy. So here's another way to look at it in SI units. So those are the mass of the 6 particles in kilograms. And again, you can get that off your reference table. 2 protons at 1.67 times 10 to the negative 27th. Add them all up. Here is the mass of that helium atom collectively. So there's my mass deficit. That's my difference in mass. Now, it's not the mass that's converted to energy. It's the difference in mass, the delta mass. So we put this E equals mc squared. That mass deficit is going to give us that much energy. So if I split the helium, if I was to split a helium atom into its constituents, that's how much energy is going to result from that transition.